So this video is going to discuss the heap sort. We're gonna review a little bit about heaps first, just to get a running start. So heaps have a shape and an order, left balanced binary tree, and a left balanced binary tree in which the value of each parent is smaller than both of its children. Some of these are heaps and some are not, because some of these are not left balanced. So a max heap, we conclude that the largest node, the 80 in the case of this slide, is the largest node in the heap, and all the subtrees themselves are heaps. So we're going to use that fact to sort the algorithm, to sort the data elements. So there's 3 steps. Step 1 is real simple, honest. You'll see in a minute. Steps 2 and 3 use the sub-algorithm called Reheap downward. So here are in the tan box are a list of the 3 steps. Place all the items to be sorted in a left balanced binary tree. That's simple. We'll show you how that works in a second. Then build the initial heap out of that tree, because it may not be a heap. And then thirdly, swap and rebuild. Swap downward into the sorted position and rebuild it downward using the Reheap downward algorithm. So step 1, do nothing. We like that. So basically we consider the elements to be sorted in an array. And we consider it using the 2i plus 1, 2i plus 2 rule to locate the elements in a tree. Now you notice to the lower right that is not a heap, but it is a left balanced tree. So step 2, we build an initial heap. So we look at each parent in order. First of all, we start with the highest level rightmost parent. Now I kind of wish that 3 had children, had a leaf as well, because it looks like we're dealing with the leftmost parent, but it's not. It's the rightmost parent, 2. And continually swap it until it's larger than both its children and it becomes a leaf. So in this case, 2 is the rightmost highest level parent. And we look at the 3 elements and decide which one is largest, and that becomes 19. So there is a formula. The floor of n over 2 minus 1 is the highest level rightmost parent. So here's a discussion of the whole, of building the whole heap. At the top, first we start with 2. We swap 19 into position 2 to make it into a heap. And then we go to the rightmost highest level remaining parent. We've already dealt with 2. So we go to 36. That's the next parent, rightmost highest level parent. And we see that 100 is greater than 36, so we swap it in. Then we go to the next highest level rightmost parent, and that's 17. And we swap 17 with 19, and then we have to compare 17 with the rest of the subtree, because it might be that 17 is less than the 2 children, the 2 leaves. Suppose instead of 7 we had 18 there, then 17 would have to go down 1 more. So then we go to the next rightmost highest level parent, which is the root, happens to be the root, and we swap it down to 100, and 25 swaps down to 36. Now at the bottom is a different representation of this process. You can draw it out, or you can build the table, or you can do both. So notice that the left element is the unsorted non-heap initial array. And we swap 2, 19, and 7. We compare those three, and we swap 19 and 2. That's the gold. The gray is the comparison, the gold is the swap. And then we go to 36, and we compare 36, 101. We swap 136, that's the gold. And then we can go to the next element, which is 17, 19, and 3. And in this case, we compare and swap both. That's why it's blue. We swap 19 and 17. And then we go on one further and swap 100. And that becomes the final heap. And it is a left balanced binary tree heap. So that's step 2. Here's another example of step 2. We have this array, and we want to find the last parent, the final parent, the parent of the last child is child minus 1 divided by 2, child index, which is 65. So that's the last child. The parent is 10 minus 1 is 9 divided by 2, which is 4. And that's 56, which is also the parent, the rightmost highest level parent. So we look at the children, find the largest, and we swap 65 up to in place of 50. And then we find the next element, which is 3. At this point, we go 4, 3, 2, 1, 0. So we find that 92 is the largest, so we swap it. We go 72, and it's already the heap. We go to 60, and it swaps with 92. So you have to swap it, reheap downward to 70. Now we check the last parent, 15, and we swap with 92. And that's not a heap, so we swap 15 downward with 70, 15 downward with 60, and that's the heap. So this is the reheap downward algorithm. If P is the root node of a tree or subtree, whose subtrees are already heaps. If P has no children, then you're done. If P is greater than both their children, then you're done. Otherwise, step 4, swap P with the greatest child. And then keep repeating until P is now the root. So step 3 is to turn this heap, sort this heap. So the first thing we do seems a little backwards, but we swap 100 with the last element in the array, or the rightmost highest level leaf. So we swap 100 with 7. Now obviously the 7 being at the root does not make it a heap. What do we do with the 100? Well, we put it down there at the bottom, and we don't consider it anymore because that is the highest, the maximum element in the list. So we rebuild the remaining elements into a heap, and we do it this way. Swap 7 with 36, and then 7 with 25. So here's a couple passes through. Notice that 100 swaps with 7 like we showed on the previous slide, and then 100 is fenced off at the bottom. It's also fenced off at the bottom of the table, And notice if 100 goes all the way now, we never touch 100 again. Eventually 36 gets in there as the second most highest level element in the list, and then 25, and then 19, and then 17. Now you can't really see it, but there's a bold line that shows the fencing off of these elements. So here's an example of a heap, and we take the last element, 8, which also incidentally is the last element in the array, and we swap it with the root, and we put 70 down below, but 70 is now fenced off because it is the largest. And now we swap 30, the next last, after we've reheaped downwards and turned this new array into a new tree into an array, into a heap. We swap 30 with 60. Then we swap 40 with 8, and turn it back into a tree, and then swap 12 with 30 and 8. So that is the algorithm for sorting. And notice this, let me back up one. This is now a sorted array from top to bottom. From bottom to top, it's sorted, from top to bottom, it's sorted smaller first. So what's the sort effort? The sort effort is shown here, the swaps and rebuilds. The swap effort is less than n times the floor of log n times 2. So the sort effort is order n log n. And the number of swaps is less than n log n, so it's overall the algorithm is order n log n.